Okay, well, why are logarithms important? Well, they're important for a couple of reasons. One reason is that if you have something like hearing, my hearing, well, let's not use me because my hearing is pretty bad. But if you take a healthy child, the faintest sound they can hear is about 1 trillion times less energetic than the loudest sound that they can stand without hurting their ears. So you have a human range of perceptible sounds, some of which are 1 trillion times bigger than others. Perceptible sounds that don't hurt your ears. You can go louder, but it hurts your ears, and you try to get away from it. Okay, if then one sound is 48 billion times greater than the other one, what's that tell you? You can't visualize 48 billion. Well, we don't perceive some sounds as being 48 billion times greater than others, but I could easily make two sounds if I talk quietly. And then if I was to yell, but there are people in the hall and I don't want to alarm them, you would hear a sound that's 10 billion times. That doesn't sound 10 billion times more. Might sound 50 times, but not 10 billion. Well, actually, on our decibel scale, 10 billion would be like 90 times louder, okay? And 48 billion would be like 95 times greater, actually 96 or 97, okay? Maybe, yeah, about 97. Okay, well, you don't have to know how to figure that out. Just, that's one example, and we use logarithms to do that. So if one sound is 48 billion times louder than the other, we take the log of that 48 billion and we multiply it by 10. And that's how many times louder we say it sounds. Now, that's an imperfect model, but it gives us a more intuitive grasp of those big numbers, because the numbers then go from 0 to 120. We can visualize that scale. We can't visualize a scale from 0 to 1 trillion, or from 1 to 1 trillion. Now, that's one application that I didn't talk about in class, so you get this little bonus to think about. We will be talking about it. But here, we have an equation. Now, you don't know why an equation like this would arise, but they do arise a lot, okay? Where your exponent, it contains your variable that you're trying to solve for. You've got an equation, you want to solve this for t. The t's up here in your exponent. You can't use a distributive law to get rid of it. You can't multiply by something. You can't divide by something. Anything you do, if you understand the laws of exponents and apply them correctly, is not going to work. The only thing that's going to work to solve this equation is if you take the log of both sides. So, we take the log of the left-hand side, and that should be equal to the log of the right-hand side. Now, some people think, well, we multiply by the log. Well, a log isn't a number. We can't multiply by it. We apply the logarithmic function to both sides. We form the composite of this side inside the log, or this side with the log, okay? And that's what we're doing. We're actually forming a composite. Well, anyhow, the log, what's the log of 10 to the 4t minus 5? Well, the log and the 10 to the power function are inverse functions. You get 4t minus 5, and voila, there is that t that was in the exponent, and it's now down here where you can get to it. And you got log of 1,000. Well, log of 1,000, you should see pretty quickly that's 3. Now, if I gave you some number other than 1,000, some number that wasn't a 1 followed by a bunch of zeros, it would be perfectly acceptable, matter of fact, necessary, for you to either go to a table of logs, and I'm not even sure they exist anymore. I'm sure you can find one, but you don't want to do that. You just punch it into your calculator. You got a log button, an LOG log button. You punch whatever this number is into the LOG, and you can right now take 1,000 and punch it in and do your LOG, and you're going to get 3. Verify. Okay. But you don't need the calculator to figure out the log of 1 followed by a number of zeros. It's just a number of zeros. Okay, well, so we apply the log to both sides and we get an equation that we can easily solve for t. Now I notice that log x and 10 to the x are inverses, exclamation point. That's the reason that this step works from here to here. Now I just copy this step down again, and now we just, add 5 to both sides, divide by 4, we get t equals 2. So now we know that if we plug in 2 for t, well, it's going to be easy to verify this. 4 times 2 is 8, minus 5 gives us 3, 10 to the third is 1,000, so we solved it correctly. Okay, the main point here is that if we got a function where our variable is in the exponent, we can get at it by taking logs. Now, there's one other important thing that I mentioned just briefly at the end of class, but you want to remember this. We've seen base 2 logs. We've done graphs of the base 2 log. We've estimated base 2 logs based on inverting the graph of the 2 to the x function, with which we're very familiar. Okay? Now, log base 2 of x, I'm telling you now, and I'm not proving this, is just log x divided by log 2. It's easy to prove this if you really, really understand the laws of exponents. Okay? But we're not going to assume that people understand the laws of exponents well enough to prove this, so we're probably not going to prove it. So I'm just going to assert it and tell you, yes, I can prove this based on the laws of exponents, and if you show me that you really understand the laws of exponents, then I will be glad to show you the proof. If I have time, even if you don't understand, I'll show you why you need to understand the laws of exponents in the process of proving it. More generally, log to any base of x is log of x divided by the log of that base. Very simple formula that allows you to solve any exponential equation. So if we wanted to solve 6 to the 3x minus 5 equals 9, okay, well, we could take the log of 6 to the 3x minus 5 equals the log of 9. We punch that into our calculator. The log of 9, I don't want to think about the approximation. This is going to be approximately negative 0.1. Now, what am I talking about? It's going to be like pretty close to 0.9. Okay? And this is going to be well, the log of 6 to the 3x minus 5 is, and there's a step that I didn't prepare you for here. It's going to turn out to be I'm debating about whether to write this out. I don't even want to write it out. You can apply this to do this, okay? And I might even possibly write it down wrong if I don't write out a lot of stuff, to be careful. I'm thinking it's going to be the log 6 times the log of 10 to the 3x minus 5. But I want to think that through, actually, okay? I want to write it out carefully, not skip steps. So we could do this. We could take the log 6 of both sides also. So we could write this as, we could write from this, we could immediately write log to the base 6 of 6 to the 3x minus 5 equals log to the base 6 of 9, which is what I should have done originally, because log to the base 6 and 6 to the power are inverse functions. Okay? We've already done enough definition of that to get that. And this is what? This is the log of 9 over the log of 6. Okay? Which is what I said, you do log of 6 times the base 10 log of this thing. So it's kind of the way I thought it would work out, but I didn't trust myself to do that. We can do log 9 with our calculator. We can do log 6 with our calculator. We get a number here. But, you know, we would generally solve this. We'd say, okay, 3x minus 5 equals whatever log of 9 is divided by whatever the log of 6 is. And we will certainly resist the temptation to divide 9 by 6 because that's not what's going on. Okay? And add 5 to both sides, we get this. I'm getting hungry. Not thinking clearly. But then we do x is 1/3 of log 9 over log 6 plus 5. At this point, we would take our calculator, divide this out, add 5 to it, and divide it by 3. Then we'd have our solution. So the solution of a logarithmic equation or an exponential equation using logs turns out to be pretty simple. And this is one thing we're doing this week. We're going to talk more about it next time. So that example, yeah, I wouldn't regard you as being responsible for being able to do that, but kind of get that into your head if you possibly can before we talk about it on Thursday.